Let me start recording. So what do you mean? All of you know what is specific heat? So if I write C, okay, C is symbol of specific heat, okay, and I write dq by dt, right? Dq is the heat and temperature. So any body if we heat, okay, so the temperature required to increase the temperature of body, especially crystalline solid we are talking about here, crystalline solid, okay. So if I want to increase the temperature by 1 degree of a crystalline solid, how much energy I require, okay, that is called your specific heat, okay. And so you can write, okay, specific heat. So dq, what is dq? So dq is heat required to increase, okay, to increase the temperature of solid, okay, of solid by 1 degree Kelvin, okay. So that is a specific heat, okay. Now specific heat, all of you know, specific heat generally two type, the way we measure it, okay. So specific heat is two types. One is, what are the type of specific heat?
Latent heat, specific heat at constant temperature and constant pressure.
Okay, so specific heat at constant volume, okay, specific heat at constant volume, okay, and specific heat at constant pressure, okay. So if you heat a sample inside a closed container and then you measure how much heat is required to increase the temperature of the solid, okay, is solid, okay, that will be specific heat. So the difference between specific heat in solid and liquid, okay, there is a very less difference. If you take the example of gas or a liquid, then there will be difference between Cp and Cv, okay. So Cv is what? Cv is your specific heat at constant volume, and Cp is your specific heat at constant pressure, okay. So in the case of solid, okay, you can assume both are same. Very little difference is there in these two terms, okay. Now
please repeat this type once again. You were not audible my side.
Okay, so I told specific heat is two type, okay. One is specific heat at constant volume, and other is specific heat is at constant pressure, okay. And you have studied this thing in your thermodynamics, okay. The difference between Cp and Cv is how much for ideal gas? R, okay. And if you take wonderful gas, then difference will be then the expression is different, okay. But in the case of solid, okay, Cp and Cv are almost same, okay, because solid already volume is fixed. Now if you're heating, so volume expansion is very low. So if you remember, you may have done that in your thermodynamics course. Then Cp minus Cv for solids given by 9 alpha square, okay, B Vt, okay. So beta is compressibility factor, alpha is the expansion coefficient, okay. So these are very negligible in the case of solid, okay. So for solid, there's a very less difference, okay. Now if I take Cv, okay, if I take first law of thermodynamics, it says dq okay equals to du plus pdv, okay. Now I want Cv, okay. Cv is nothing, that is dq by dt at constant volume. So if I take volume constant, this become what? Du by dt, because dV is 0. If I take constant volume, dV will be 0. So if I take dQ by dt, so my specific heat is equal to differentiation of internal energy with respect to temperature. Okay, so if any solid I want to measure the specific heat, the first thing I need to calculate is internal energy. Okay, and here internal energy mainly I'm talking about the vibrational energy, okay, of solid. So let us calculate. Now there are three models which explains the specific heats of solid. Okay, so shall I erase this one? So if I see the experimental curve, okay, of specific heat, experimental values for solids, experimental values of specific heat of solids, okay, crystalline solids. So if I see the experimental graph, okay, between CV and temperature, okay, so this graph is very like this, okay. So this is at low temperature, okay, at low temperature, and this is your at high temperature, and the value of specific heat at high temperature is 3R constant. Okay, so at high temperature you have CV values, okay, equal to 3R. So the specific heat of solid is constant 3R at high temperature. At high temperature, okay, so CV equals to 3R, where R is what? R is your gas constant whose value is 2 calorie per degree Kelvin, okay, per mole. This is a molar specific heat. Molar specific heat is 3R, okay, so that is equal to what? So your CV become 6 calorie per degree Kelvin per mole. So in order to increase the temperature, okay, of 1 mole by 1 degree, you need 6 calorie energy, okay, of solid, and that is fixed. So at high temperature is fixed, and if you fit this data at low temperature, then your CV is proportional to T cube. So at low temperature, CV varies as a T cube, and at high temperature, CV is 3R. Okay, so that point you need to remember. Okay, now there are different models of solid which try to explain this experimental curve. Okay, so we'll take these different models one by one and discuss how successful were they, how they were able to explain this curve, these curve. Okay, so first we'll say classical model. Okay, there are three models. Okay, so first is called classical model. Okay, and the specific heat of solid at high temperature is constant. Okay, so this is also called, okay, Dulong-Petit law. Okay, this is called your Dulong-Petit law. Dulong-Petit law. Okay, that specific heat at high temperature is constant. Okay, that is your Dulong-Petit law. Now we'll take one by one model, okay, and see how this model can explain the specific heat. Okay, so first is classical model, second is Einstein model, and third is your Debye model. Okay. So the line is very clear. Okay, if I want to calculate the specific heat, I need to calculate the energy. Once I energy, I need to differentiate with respect to temperature. So you'll get the specific heat. Okay. So now classical model says that all the atoms vibrating in solids, okay, are equivalent to 3n one-dimensional harmonic oscillator. Okay. So a solid, okay, is equivalent to 3n one-dimensional harmonic oscillators. Classic harmonic oscillators. Okay. Three one-dimensional classic harmonic oscillators. Okay. So this is the one point. Okay. So, and he says all the atoms vibrate independently. All the atoms vibrate independently. This is assumed. Okay. Now, if I want to write the total energy of one harmonic oscillator, what is the total energy of one harmonic oscillator? How can I write the energy? All of you understand what is harmonic oscillator?
Half of m omega square
Okay.
plus half of k square.
And okay. So harmonic oscillator means it has a two type of energy. One is kinetic energy, one is potential energy. Like your particle is attached to a spring, that is harmonic oscillator. Okay. So harmonic oscillator has the expression of energy is what given. Harmonic oscillator energy kya hai? Average energy of one harmonic oscillator. Okay. That will be px square by 2m and half kx square, and you can write m omega naught square x kx square. Okay. So this is and the energy of, so how many degree of freedoms are there in harmonic oscillator? Harmonic oscillator में degree of freedom कितना होता है?
So 2.
Okay. So there are two quadratic terms, two square terms in energy expression. तो क्लासिकली किसी भी सिस्टम की क्लासिकल एनर्जी एक्सप्रेशन में जितनी भी स्क्वायर टर्म होंगी, ओके, दैट विल बी इट्स डिग्री ऑफ फ्रीडम. सो if you have a quantum harmonic oscillator, its degree of freedom is 2, not 1. Okay. If your particle is in square well, like in particle box, then it's a degree of freedom 1, because you don't have potential energy. It is free. It's only restricted in one dimension. Okay. But to quantum harmonic oscillator, the energy is, the degree of freedom is 2. Okay. And classical partition theorem, equipartition theorem says that for each degree of freedom, their energy is half kT. Okay. So you must have read. Okay. So there are degree of freedom 2. Okay. So I can write the energy of 1D harmonic oscillator. This is a 1D harmonic oscillator. For 1D simple harmonic oscillator or 1D harmonic oscillator. So its energy will be 2 degree of freedom, and each degree of freedom, the energy is half kT. So half kT. So classically, the energy of harmonic oscillator is kT. Generally, exam से question आता है, सब लोग half kT लिख के आते हैं. So classically, your energy of harmonic oscillator is not half kT, it is kT. Okay. Now in solid, we have n atoms. Okay. And each atom is equal to 3 harmonic oscillator. It can move in three dimensions. Okay. So solid is equivalent to 3n harmonic oscillators. So the energy of solid will be how much? 3n kT. So the total vibration energy of solid. Okay. Total energy, vibrational energy of solid, okay, it is equal to what? 3 kT. N is a number, 3 kBT. Okay. And the energy of 1 mole, okay, if I want to try energy of 1 mole, energy of 1 mole solid, okay, say U, that will be molar energy. So that will be your what? Instead of N, in 1 mole, there are Avogadro number atoms. This will be total energy. Okay. Now I need to calculate specific heat. Okay. So if I want to calculate,
Can you explain how harmonic oscillator has 2 degrees of freedom?
So harmonic oscillator has a see any energy expression, you count the quadratic terms. Okay, you count the quadratic terms. So I return the energy, kinetic energy square, px square and x square. So there are two square terms. Okay, there are two square terms. So in the energy expression, the number of quadratic term present is equal to the degree of freedom. Okay, so that's why I'm writing here degree of freedom is 2. Okay, so now if I want to write specific heat, okay, so specific heat, what will be here? Specific heat will be here del U upon del T, temperature variation. Okay, so if I divide by temperature, this will give you 3 Na kb, and 3 Na kb is equal to R. So this becomes 3R. Okay, so this is 3R. So that's what, so your classical model says that the specific heat of solid is 3R. Okay, or roughly equal to 5.96. I told you 6, it is equal to 5.96. okay, calorie per per Kelvin per mole. Okay, so this is your specific heat. But so model says that specific heat is constant, but we seen experimentally your specific heat is constant only at high temperature. So this model is not saying anything about low temperature. Okay, so it is quite well agreement with your experimental data of specific heat at high temperature, but at low temperature it is not able to say anything about this model. Okay, so this was your classical model. Okay, let me discuss the second model. Second model is your Einstein model. Okay, second model is your Einstein model. Okay, so can anyone tell what are the, now the same track will follow? We'll calculate the energy of solid and we'll differentiate
Degree of freedom.
yes. Okay, so let me discuss Einstein model. Okay, so in Einstein model, okay, so Einstein model is also same. It also says your atoms are harmonic oscillator. Okay, instead of classical, now it says quantum harmonic oscillator. Okay, so he says, okay, the atoms of solid, the atoms of solids are quantum harmonic oscillator. Quantum harmonic oscillator. Okay, and this says all atoms, like classical model, all atoms are vibrating, okay, with single frequency, with same frequency or single frequency. All atoms are vibrating with same frequency. Okay, so this is too important. Now we know the energy of a quantum harmonic oscillator is given by what? n plus half h cut omega. Okay, so here what I'm saying, I am only taking nh cut omega naught. In single frequency, they are vibrating with single frequency. I'm not taking n plus half, because when you take n plus half, so you get some term which is constant, and when we will differentiate with temperature, that term will disappear. Okay, so you can use n plus half also. So there will be final answer, there will be no change. Okay, so I am doing this derivation with En equals to nh half h cut omega. You have to do, you this homework, you try this one. Same with only one term, n plus half h cut omega naught. Okay, so there will be no difference. Okay, and where n is what? N is 1, 2, 3, so on. Okay, if you want n, you can put 0 also. Can you put n 0? Can you put n 0?
No, sir, energy will be 0, na? Energy will be 0.
Okay.
What we will calculate in that case?
Okay. So let it we write 1 2 3. Okay, so if we use n plus half h cut omega, that time we can put n is equal to 0 also, so that you can try with that one also. Okay, so so this is the assumptions. Okay, so now let us calculate the energy of solid. Okay, so can I erase this one? Okay, so now
Yes.
let us calculate the energy of solid. Okay, so if we want to calculate the energy of solid, okay, so we know that the number of atoms, okay, in any state, okay, that is given by what? Exponential an upon kt. Okay, if I use Maxwell-Boltzmann statics, okay, so the nn will be what? N0 exponential. If I want to calculate total energy, okay, so total energy will be what? Total energy will be so here en is what? En is nh h cut omega naught. Okay, total energy will be what? Total energy, or if I want average energy of a harmonic oscillator, so how can I write average energy? Can anyone tell? Average energy means what? Total energy divided by total number of atom. Okay, so total energy, how can I write? So n equals to 1 to infinite. Okay, suppose in level 1 there are n1 atom, level 2 there are n2 atoms. Okay, so this is nn and the energy of en. Okay, suppose one atom there, so n1 number of atom present in level 1, n2 number of atom present in level 2. Okay, so you multiply this thing, this will give you total energy. Okay, and if you divide this total energy by total number of atoms, so n equal to 1 to n, so this will give you what? This will give you average energy of particle. So what we'll do, we'll calculate average energy, and we know there are 3n harmonic oscillator, 3n harmonic oscillator, so we'll multiply by 3n, and then so first we'll calculate average energy of this your phonon. Okay, so this is what we're calculating, vibrations. Okay, basically this is the average energy of phonon, what we're calculating. This is the average energy.
Sir, in this case, we can't use a degree of freedom, or approach is different. Okay.
No, this is approach is different. Huh? Okay, so now we have to calculate this expression. Okay, and we know this is that is classically we know the energy is half kT. Okay, that approach we can apply here. So we don't know what is the freedom energy here. Okay, that's why applying here.
Here,
yeah,
nn is what?
Number of particle in state n. Okay, number of particle having energy en. Number of particle, and n0 is ground state. Okay, how many particles are in 0 state, ground state? Okay, so this is Maxwell-Boltzmann statics. Okay, so let it be clear in 1 minute. Okay, so if I write this one, so this will be my ink finished today. Okay, so this. Okay, so now if I want to open a nn, okay, so en is en, and nn is what? Nn is your n naught exponential minus en upon kt. Okay, and this is here what? N equal to 1. So this is your n0 exponential en by kt, kbt or kt, whatever you want. Okay, kbt or kt. So n0 will be cancel. Okay, so you will be having what? You will be having n equal to 1 infinite en exponential minus en upon kbt. Okay, and here you will be having remaining n equal to 1 to infinity exponential minus en upon kbt. Okay, so now that expression we need to solve. Okay, so are you able to see this now, what I'm writing? Are my expressions are visible now? What I'm writing?
Yes, sir.
Okay.
Yes, sir.
Okay. So let us now calculate the total energy. Okay, average energy of harmonic oscillator. Okay. So now if I want to write harmonic energy, okay. So what I can write? Okay. So what is saying? They're saying the limit is 0 to infinite. Okay. This limit is 0 to infinite. Why it is saying? Okay. Okay, let it write the limit. I'll explain what is happening. Okay, let me check. They are saying the limit is 0 to infinite, not because the probably no what no I'm telling what now. The actual expression is what actual expression is your n plus half h cut omega naught. Okay, so here your n is expression is same n start from 0. Okay, but since I have just for simplification of calculations, okay, I didn't consider this half term. Okay, so that's why and the limit will be same, but just for simplification I didn't consider this one. Okay, so you have to put the limit same n equal to 0. You can try with this expression also, same आएगा. अभी देखो मैं check बता दूंगा अभी. Okay, so you write n0 equals limit, you please change. Okay, now just put the values. Okay, put the values here from n is equal to 0. So so we have average energy E, okay, is equal to n is equal to 0 to infinite. Okay, En is what? And h cut omega naught exponential minus n h cut omega naught upon kbt. Okay, and this is what? And
one
exponential. हाँ बोलो. And
one
नहीं वो एक्चुअली एक्सप्रेशन में तो वही तो बोला मैंने. एक्चुअल एक्सप्रेशन में तो 0 ही है ना. वो मैंने हाफ हटा दिया है क्योंकि वो एक हाफ आपको रखना है भाई. आप समझ नहीं रहे हो. वो आपको यहाँ पर रखना है पर क्योंकि वो डिफरेंशिएट करने से कट जाएगा, लास्ट में कैंसिल हो जाएगा वो टर्म. समझ रहे हो ना.
अच्छा ठीक है.
वो कैंसिल हो जाएगा तो इसलिए मैं लिखा नहीं. आप चाहो तो हाफ हाफ लगा करो, लिमिट ये लगाओ, लिमिट में चेंज नहीं आएगा. ठीक है, फिजिक्स थोड़ी चेंज करेंगे. क्योंकि ये एक्सप्रेशन सिंपल हो जाएगा सॉल्व करना मेरे लिए. वो भी आसान नहीं है, वो भी करके देखना. एक एक्स्ट्रा टर्म आ जाएगा और कुछ नहीं होगा. ठीक है. सो नाउ if I put the limits here, okay, if you put 0 here, so what will become 0. If you put 1 here, okay, so what will become exponential minus h cut omega kbt. Okay, and then if you put 2 1, you put 1, 0 पूरा 0 का term. I'm opening this expression. If you put 2, so n equal to 2 h cut omega naught exponential minus 2 h cut omega kbt. Okay, then so on, keep on opening like this. Okay,
फर्स्ट में भी आएगा ना h cut omega naught फर्स्ट टर्म में 1 रखेंगे वहां.
हाँ, h cut omega naught कॉमन निकाल लो आप लोग. h cut omega naught कॉमन निकाल लो सब में से. Okay, so this become 2 exponential, that's 3 exponential. Okay, and similarly you open this one, so what you get? You put 0, so this become 1. Okay, if you put 1, so this become exponential minus h cut omega kbt. Okay, and put 2 exponential minus 2 h cut omega kbt. Okay, now let x is equal to minus h cut omega naught kbt. Say this is my x. Okay, so if you put these values here, so my average energy, okay, my average energy will be what? So this is, so I'm putting this value equal to x. Okay, so this become what? E power x, exponential x or e power x. Okay, this become e power 2x, then e power 3x. Okay, so on. Similarly, if I write bottom one, so bottom will become what? H cut omega bhi hai. You have h cut omega naught bhi hai. Okay, and bottom you have 1 plus ex. हाँ
2 भी है ना, 2 3
क्या
कोएफिशिएंट आएगी ना ऊपर,
कौन सा
2
वाला?
कोएफिशिएंट.
हाँ 2 भी है,
सेकंड टर्म
2 भी है, हाँ 2 भी है, यहाँ 3 भी है. थैंक यू. ओके, सो 3 e power 3x, so on. Okay, so now if you solve this one, okay, very easy to solve this one. Okay, so I can write my energy E equal to h cut omega naught. Okay, and this expression I can write d upon dx of 1 plus ex e upon 2x, so on, 2x plus e power 3x, so on. So now if you differentiate, okay, this term ln, okay, log of 1 plus ex plus e power 2x plus e power 3x. Okay, so now if you differentiate, so this will come 1 plus ex plus 2x, and again you do differentiate this one. So this 0 e power x, this will come 2 e power 2x, this will come 3 e power 3x. Okay, I hope this expression is clear to you.
Yes, so it is clear.
Other students,
Yes, sir.
are you okay with
Yes, sir.
this expression? Okay, so if I write e bar,
Sir, please explain once again.
I just now asked. See, this is d by dx of ln of 1 plus ex. So if I differentiate this one, so ln x will be 1 by x. Okay, ln
Yes,
x will be
sir.
1 by x. So 1 plus e, this will come 1 plus this one. This expression will come. Okay, and then you have to differentiate this one. So once you differentiate this one, so 1 is 0, e power x, e power 2x will be 2 e power 2x, e power 3x will be 3 e power 3x. Okay.
Yes.
So this expression, so I have 5 marker, nothing is working, and unfortunately my ink also finished today. Okay, so now so this is the expression to you. Okay, now so solve how to calculate the energy. How can we calculate energy? Okay, so now what I can do, tell me, how can I solve this one? So I have h cut omega naught d upon dx ln, this is geometrical series. Okay, so what is the sum of this series? What is sum of this series? If you have a 1 plus x square plus x cube, what is the sum of this series?
1 plus x raised to n.
No, the geometrical series.
1 by 1 minus x.
E into 1 minus Rn. That we
Okay,
have to-
1 upon 1 minus x. Okay, suppose you have a series a plus r square. Okay, so that is r a r say so 1 plus r square. So this expression is called 1 upon 1 minus r, na? Do you remember or not remember geometrical series? Are you okay with this expression, what I'm writing?
No sir, actually geometrical series याद आ रहा है, Poisson का formula नहीं याद आ रहा.
So what I can remember, you should remember this formula, na? Okay, if this series is here, what is the actual formula? How do you write actual formula?
A minus Rn upon something.
If there are n term, okay, if there are n term, what is the formula? And if it's the infinite term, what is the formula? Anybody can remember geometrical series?
A upon 1 minus r to the power n.
A upon 1 minus r to the power n. Okay, this is for infinite series. Okay, this is for infinite series. So here A is what? A is our 1. Okay. So you can write a upon 1, a upon 1, that will be a upon 1. In fact, for infinite, this is a upon 1 minus r. For r terms, something is there, 1 minus rn upon something is there. Okay. So infinite time, this is a upon 1 minus r. Okay, you can check it on internet. Okay. So now I'm writing. So that will be what? 1 upon
1 minus e to the power x.
1 minus e to the power
x.
Okay. Now differentiate this one. So h cut omega naught. Okay. Now if you differentiate this one, so this will give you what? 1 minus, what should I do first? 1 minus ex. Okay. And then 1 minus ex, and then you 1 by 1 you do, so 1 minus e minus x ka whole square. Okay. So what will you get? Minus h cut omega 1 upon 1 minus ex, or so what I can write now? E upon
Sir, और एक e to the power x है.
e to the power x आएगा एक बार ना, माइनस का ना, so प्लस e to the power x आएगा. Very good. So you have e to the power x.
नहीं सर, I think माइनस ही आएगा. माइनस
क्यों माइनस क्यों आएगा अभी? या इसका करेंगे, जब उसका कर रहे हो तो इसका करेंगे तो माइनस नहीं आएगा, इसकी वाला माइनस. ये तो पहले तो मैंने 1 by x का किया.
yes sorry.
Okay. So this is 1 upon 1 minus ex. Okay. Now you divide this one, so this will become e power minus x, e power minus x minus 1. So are you people are comfortable with this expression what I'm writing or not? It's simple mathematics.
Sir, h cross omega naught भी आएगा ना?
हाँ, h cross भी आएगा. h cut omega naught. h cut omega naught. Are you comfortable what I'm writing? Okay. It's yes. Very simple calculation. Okay. So this will be what? Your h cut omega naught. Just put the value of x. So this become what? H cut omega naught kBt minus 1. Okay. And this is the very important formula, average energy of quantum harmonic oscillator. Okay. Or better to remember, average energy of phonon. Okay. Average energy of harmonic oscillator, quantum harmonic oscillator, or average energy of phonon. Okay. So now, once you know the average energy, now it's very easy to calculate the specific heat. Now in 1 mole of solid, you have a Avogadro number of atoms. So total energy will be what? 3 Na. Okay. E. So this will become what? 3 Na h cut omega naught. Okay. E h cut omega naught kBt minus 1. Okay. This is total energy. You say U, total energy use. Okay. You use same expression. So in the beginning, I took average the quantum energy NH h cut omega naught. If you take half also, so then only one term will become more. Okay. If I take this half also, so I told you that is homework. Okay. So I use this expression. If you use other expression, okay. So there will be difference of half. So I got the average energy of this one. If you use half, then you will get an average energy of this one. Okay. H cut omega naught. Okay. Plus h cut omega naught. E h cut omega naught kBt minus 1. If you use n plus half h cut omega. Same exponential you do. Same series will form. Okay. Only first term will change. Well, yeah, one that there will be some e power minus x something, x by 2 something. Okay. So if you use that formula, you will get the average energy this one. Now when you multiply, this term will multiply by 3n, and when you differentiate, this is constant, so it will be 0. So that's why instead of using n plus half, I used what? N h cut omega naught. Okay, so there is no difference. So now you have the energy expression. Okay, now just you need to calculate the specific heat. Okay, so if I now on a specific heat Cv, okay, that will be what? Del U upon del T. Okay, so before I calculate this specific heat, let me calculate when, let me define this h cut omega naught kBT. Okay, h naught h cut omega is equal to theta. Let me just check. Okay, so let me solve this one. So say at high temperature, okay, at high temperature, what will happen? This term, if I take temperature is high, okay, if this temperature is high, so then h cut omega naught is less than kBT. Okay, so this term is less than 1. Okay, so I can write this term as a E h cut omega naught kBT. I can expand, this is a 1 plus x h cut omega naught kBT. Okay, at high temperature limit. So now if I write energy at high temperature U, that will be what? 3 Na h cut omega naught, okay, divide by e power h cut omega naught kBT minus 1. Okay, so this will become 3 Na h cut omega naught. Okay, and we open this one, so this will become 1 plus h cut omega naught kBT minus 1. So minus cancel. Okay, h cut cancel. So again this will become what? 3 Na kBT, that is equal to 3R. So again at high temperature you're getting the specific heat is equal to 3R, like same like a classical model. So Einstein model also is able to explain you the specific heat. Okay, so experimentally also we getting 3R. This model also says that high temperature your specific heat is this one. Okay, this is total energy, and if you divide this one by you get Cv du by dt. Okay, you'll get what? 3 N kb, that is 3R. Okay, now we have to see at low temperature. Okay, so are you people comfortable with this thing? Are you getting what I'm doing here? So I am calculating total energy. So in order to calculate total energy, first I calculated the average energy. Once I know the average energy, now I know there are in solid, there are 3 N, one atom of solid is equal to 3 N harmonic oscillator. So I multiply it by 3 Na. Okay, I got the total energy. Now I applied the high temperature limit. Okay, I got this 3 N energy is equal to 3 N kBT. I differentiate with this temperature, I got 3R. Okay, this is what I get experimentally. Okay, so your Einstein model is able to explain the specific at high temperature. Okay, now let us solve this for low temperature. Low temperature. Okay, if low temperature is there, then your h cut omega naught is greater than kBT. Okay, so now I have energy, what? I have energy 3 Na, okay, h cut omega naught, okay, E h cut omega naught kBT. What is the expression? Minus 1. Okay, is this the expression of total energy? Yes. Okay, so this is total energy. Now I want specific heat. Okay, so what I can do, if I want a specific heat, just differentiate this one, C del U upon del T at constant volume. Okay, so this will give you 3 Na h cut omega naught. Okay, if you differentiate this one 1 by x, you get e h cut omega naught kbt minus 1 का whole square. Okay, whole square. And if you further differentiate this one, so you get e h cut omega naught kbt. You can do here also, no issue. Here also you can do same thing. Okay, here if so now I just put the limit here. Okay, so now this term is greater than 1. This term is high, so we can neglect 1. So if I neglect 1, my c will come what? 3 na h cut omega naught. Okay, so this power 2, so I get e power minus h cut kbt, isn't it? Okay, and if I define h cut omega naught equal to kb theta e, where theta is the Einstein temperature. Okay, so I can write this term as, you can put the approximation in an energy term also, then also you'll get same thing. So you'll get Cv equal to what? Cv is equal to 3 Na h cut omega naught. Okay, exponentially, if I write h cut omega naught by kb, h cut omega naught kb is theta e, so this becomes theta e upon T. Okay, so this is the expression for specific heat, okay, at low temperature. Now
जब हम डिफरेंशिएशन करेंगे ना तो h कट ओमेगा नॉट अपॉन kb ऐसा एक फैक्टर आएगा ना.
हाँ वो भी आएगा. हाँ वो भी आएगा. वेरी गुड. तो सो करेंगे तो क्या आएगा? विल गेट दिस वन आल्सो h कट ओमेगा नॉट kbt का स्क्वायर. दिस टर्म विल कम
kbt
स्क्वायर नहीं आएगा ना.
जस्ट लेट मी चेक.
kb आएगा सिर्फ. स्क्वायर कैसे?
बे t 1 by t है ना.
हाँ सर, तो उसका जब
सही तो है ये. kbt आएगा और माइनस मुझे करने दो. मुझे करने दो एक बार. भी इसको करो पहले. So you will get what? X square. Now if I do exponential, you get this one. Okay, now if you do this one, so you'll get h cut omega naught kb. Okay, and 1 by t करोगे तो माइनस का 1/t स्क्वायर. ओके, एंड इसका एक माइनस पहले से था ना, जब मैंने इसको किया था 1 by x को किया था, तो माइनस पहले से था एक था कि नहीं था जो. सो ये माइनस आपका पॉजिटिव हो जाएगा. ओके, so what you'll get 3 Na. Okay, this is what h cut omega naught. Okay, this becomes square h cut omega naught upon t. Okay, kbt, this becomes square, t also square. 1 kb should come more. 1 kb should come more, no? Okay, so what I'll do now, 3 Na kb. Okay, 3 Na, I am multiplying 1 kb here, I am multiplying kb here. Okay, so this will become what? This will become h cut omega naught kbt square. अभी ठीक है?
Yes sir.
हाँ, h cut omega naught kbt. I think now it is correct. Okay, so this is wrong. Okay, now if I write the final expression, I will be having
डिवाइड में से स्क्वायर की टर्म रहेगी ना.
कहाँ पे?
डिवाइड में स्क्वायर की भी टर्म रहेगी ना. h का e रेज़ टू h प्लस ओमेगा नॉट kbt माइनस 1 ब्रैकेट स्क्वायर.
ये वाला ना?
नहीं सर, ब्रैकेट स्क्वायर भी रहेगा ना.
हाँ, ये वाला ना?
नो एक्चुअली
ये वाला नीचे वाला बोल रहे, नीचे वाला.
हाँ,
तो वो तो टेम्परेचर लिमिट लगाया तभी तो माइनस आया. भी आपने if you have a high temperature, low temperature limit, then this if you low temperature limit, this expression e h cut omega naught kbt is greater than 1. Okay, so this becomes square.
Okay.
This square, so this is cancelled. That's why it's coming minus, na? Are you getting what I'm saying? This I'm applying. Let me do again. Okay, let me do it all the thing again. You people are not getting. You're not doing differentiation also. Okay. So what we have, we have U. What is the value of U? 3 Na h cut omega naught. Okay. E h cut omega naught upon kbt minus 1. Okay, this is my expression. Now I am differentiating this one. So del U upon del T, that is equal to CV. Now first I will do differentiation of this one. Okay, this will come what? H cut omega naught kbt minus 1 whole square 3 Na. H cut omega naught is already there. Now I have to do this exponential term. So this will give me what? H cut omega naught kbt. Okay. Now this term will give me h cut omega naught kb constant minus 1 by t square, and here also minus is there because when I'm doing 1 upon 1 minus 1 upon x minus 1 I'm doing. Okay, so this should come power. So minus minus, now this minus minus plus. Okay, so now what I'm multiplying here kb is there. I want to make kb square so that I can make h this square. So I'm multiplying by kb here. So this becomes 3na kb. Okay, and this term is I have E h cut omega naught kbt. Okay, we have E h cut omega naught kbt minus 1 square, and this term we have h cut omega naught kbt square. Okay, now this CV become, okay, 3 Na kb. Okay, now h cut omega naught kb, I'm writing theta e. So this become e power theta e power t. Okay, this become theta e power t whole square, and bottom we have e power theta e by t minus 1 whole square. Okay, now when I'm applying low temperature limit, so in low temperature limit, okay, in low temperature, okay, e power theta e t is greater than 1, because this is a low temperature, so this term is greater than 1. So this is greater than 1, so I can neglect this one. So now this becomes t power 2 theta e, here power theta e. So I will be left with 3 Na kb e power minus theta e upon t. Okay, theta e upon t square. This is the final expression. Okay, so now this expression says, because this expression says your specific heat is proportional to what? E power minus theta e by t, because at low temperature this factor will dominate compared to t square, which is exponential term. Okay, so it says at low temperature your specific heat will decrease exponentially. Okay, so that is better than your classical model. Okay, in classical model says that your classical model doesn't say anything about the low temperature dependence of specific heat. Okay, while in the case of Einstein model, at least we are getting some dependence, and that dependence is exponentially. While originally if we see the experiment, it says CV where it says T cube. Okay, so this model says, so if I plot this model, okay, if I plot this model, okay, CV versus temperature, okay, so this will give me this kind of dependence. So here you get exponential dependence, t power theta e exponential dependence. The value originally is t cube, so it will decrease faster compared to experimental model. At high temperature you're getting same thing 3R, but at low temperature this model is not able to explain the variation of specific heat. Okay, that is the difference, but it is at least better than your classical model, which doesn't say anything about at low temperature. It's saying it is varies with theta e, and theta is what? Theta is your Einstein temperature. Okay, and the Einstein temperature, what is the use of Einstein temperature? Okay, note down. The Einstein temperature sets the limit. Okay, when I say high temperature, low temperature, what does it mean? Okay, so that will be decided by your value of theta e. Okay, and theta e, just now I told you, theta is equal to h cut omega naught kb. Okay, and omega naught is what? Omega naught what? Just now we done lattice vibration. Omega naught is what?
Omega m sin k by 2.
4 beta m, maximum velocity, maximum v naught. So when I was discussing lattice vibration, that time also I told you that Einstein considers only maximum frequency. Okay, so this is that. So this frequency is characteristics of solid because it depends on what? Beta is what? Beta क्या है? What is beta?
Constant.
कौन सा constant?
Spring.
Spring constant. Okay, so that is different from different material. Okay, m is what? M is what?
Mass of atom.
Mass of the atom.
That is also different for this. Also varies with atom to atom. Okay, that means this is the characteristics of a solid. What is the spring constant? Okay, what is the spring constant between atom? How flexible, how strong this bonding is there? Beta. So this V naught is different for different metal. For example, if I take metals, okay, for metals or elements, okay, metallic elements, the theta E varies from 200 to 300. Okay, while this theta E, if I take diamond, it is order of 320 degree Kelvin. Now, when I say low temperature, so in this case, low temperature, anything which is less than 200 is low temperature. Here 200 itself is a low temperature. So that depends. Okay. So when I take metal case, so metal curve will be also same, but temperature range will be different. Okay. My theta E should be less than my temperature should be less than theta E. Okay. So for example, this theta E 320 for diamond. So for diamond, higher limit will be 1500, 1800. Any question? Are you getting what am I saying? Theta is your Einstein temperature that will decide your limit. Somebody mic is on, please. So that is different for different. Okay. For metal, your 500 also itself is a high temperature. In the case of diamond, that 500 will not be high temperature because it's less than your theta E. Okay, so at 500 maybe you are getting this type of behavior for diamond, while for metal you may be getting constant this curve like this. Okay, so theta
is the pulse, how much it can stay that.
So when I say low temperature, low temperature means what? When your T is less than theta E. When I say it is a low temperature. When I say high temperature, then your T should be greater than theta E. This is your high temperature. Okay. Now, if I take for the case of diamond, if diamond is 2000 for diamond, if I have a 2000 temperature, so 2000 temperature, you will get CV equal to 3R. Okay. But if you suppose that for diamond, I have 500 temperature, then I won't get this equal to 3R. Then I will be getting this slope. While in the case of metal, if I take T equal to 500, so for metal, this 500 will be greater than theta E. So I'll get constant specific heat. While if suppose I'm in 10 Kelvin, then I'll be getting this thing. I hope I made my point. Okay. If anybody has doubt, they can ask me. Any question about this? No. So I'm not getting any feedback, any response.
Sir? Sir, you in classical and Einstein model, what is the basic difference? Energy In classical, you are taking continuous, and in Einstein, you are taking discrete levels.
So in classical, I took energy is equal to half. Classically energy is distributed in the degree of freedoms. Okay. So I took the energy half kT per degree, and we calculate the energy. Okay. Here we have seen the distribution of energy using Maxwell distribution. Okay, on atoms we applied Maxwell distribution of energy and we calculated the average energy.
सर ये थीटा ई जो है ये टेम्परेचर ही है, मतलब एक तरह से
हाँ एक पैरामीटर है,
एक पैरामीटर है
दैट इज आइंस्टाइन टेम्परेचर. ओके, जो डिसाइड करता है कि जो आपको बताएगा कि रेंज क्या है. ओके, मतलब आप क्या बोलोगे हाई टेम्परेचर क्या है, हाई टेम्परेचर वो डिपेंड करता है थीटा ई उस मटेरियल के उसकी करस्पॉन्डिंग है. ओके, नॉट आई थिंक एक स्टूडेंट तो बोल रहा है. ओके, so this was your Einstein model. Okay, it varies exponentially and is constant. Okay, so now my next model is, so this model is success is that it shows high temperature variation like classical model, but it gives more insight. Okay, classical model में तो कुछ बोलता नहीं है. High temperature means what? High temperature. Okay, it at least says what is the meaning of high temperature, and it gives the variation also at low temperature, which is exponential decreasing. Okay, but exponential decreasing is not in confirmation with the experimental curve. Okay, so now in this model there was some drawbacks. Okay, which were encountered by Debye. Okay, and Debye gave another model that is called your Debye model. Okay, Debye model. Okay, so let us give 5-minute break. Okay, just drink water and again come back. So we'll discuss again. Just 2-minute break. Okay. Now let me discuss Debye model. Okay, so Debye model. Okay, the correction what suggested by Debye, that first thing here Einstein was saying that all the atoms are vibrating with single frequency. Okay, but Debye model we says the specific heat contribution comes because of low range of K values. Okay, that means for phonon curve. So we know we have seen yesterday the phonon curve. Okay, so this was pi by a, this was minus pi by a. Okay, and if you see the variation of K, okay, so my K varies like this. Okay, and then we have what? We have one more, this one. Okay, so this was your K variation of frequency. Okay, with K. This is my K and this is 0. So now these are this dispersion curve for a solid. Okay, but this is diatomic. Okay, if you are monoatomic, you'll get more branches here. So here what Debye suggests that specific heat contribution is just because of these vibrations. Okay, these vibration means low K. Okay, long wavelength regions. So whatever you are supplying energy to the solid, okay, that is only enhancing, that is consumed only by these vibrations. Okay, so specific heat is because of this longer wavelength K values. Okay, so the number one is, the assumption is the majority contribution in a specific heat. Okay, majority contribution, okay, in a specific heat. Okay, the majority contribution in specific heat is due to acoustic vibration. Okay, it is due to acoustic vibration. Okay, acoustic vibration means this branch, and this branch also we are taking only this small range where omega is proportional to K. Okay, number two, okay, this model simplifies. Okay, this model is based on simplification or linearization of dispersion curve. So my dispersion curve is omega is equal to omega sine Ka by 2. Okay, but this is a sine curve. Okay, this is sine curve, but this model says that we will not consider this full variation, we'll consider only these linear variations. Okay, so this model based on simplification or linearization of a dispersion curve, that means now I can write my omega. Okay, omega frequency is H proportional to K, V naught K. Okay, so this is my dispersion curve now for this model. Okay, here you can also write instead of okay, V naught is correct. Okay, now if I have suppose I have a 3-dimensional solid, okay, of 3-dimensional monoatomic solid. So in that case, how many branches I will have? If I have a 3-dimensional solid, monoatomic solid,
6.
कैसे?
3 will be there.
3 will be there.
3, okay, sir. 3, sir. Sorry.
3 will be there. Okay. So now I have to take this sound here. So this is my dispersion curve. Okay. But because now I will have like this 3. This will not be, obviously this will not, for monoatomic case this will not be there. I am calculating the specific heat for monoatomic. Okay. So in the case of monoatomic, this branch will not be there. This will come only for diatomic, triatomic, polyatomic atoms. Okay, solids. So if you monoatomic solids, you will get only this one. Only number will increase. So now you have 3-dimensional solid. So you have 3. Longitudinal acoustic, transfer acoustic 1, transfer acoustic 2. Okay. So now what I'm calculating here, this V naught, this velocity V naught, it is actually average of these branches. Okay, that we not use, but you should remember. So actually this V naught, what I'm using, this is equal to what? This is equal to 1 upon VL plus 2 upon VT. Okay, so what I'm using here, V naught is basically velocity of sound at longer wavelength region. So this is basically equal to 1 upon V L for longitudinal branch, and there are 2 transfer branches. So you can write 2 VT. Okay. Now it is very easy to calculate the total energy. Okay. Now suppose
Sir, numerator, what you have written in this
VT 3 upon V naught equal to 1 upon VL plus 2 upon VT. Okay.
So ये relation कहाँ से आया मतलब?
ये एवरेज है ना भी सपोज अगर VL इक्वल टू VT है तो ये क्या हो जाएगा 3/VT है 3/VL हो जाएगा। भी लॉन्गिट्यूडनल ब्रांच में थोड़ा सा वेरिएशन है ना, तो वेलोसिटी तो अलग अलग है ना। if I want to take this 3 branches na, so if I take here, suppose here energy is VL, here energy will be VT, here also energy will be VT, so there's slight differences there na. If you have to calculate slope, velocity is what, the slope of omega by k, this is what slope na, velocity is what, the slope of omega by k, that slope is different. Okay,
सर सिर्फ लीनियर रीजन लेना है सर, उसी की वजह से हम लोग जंक्शन मान के चल रहे ना, नहीं तो अगर नहीं होता।
हाँ बस हमको लीनियर लेना है, लीनियर में हमको एवरेज करना है, ठीक है। हमको
ये डिबाई के जंक्शन थी,
डिबाई जंक्शन है। ओके, तो डिबाई फर्स्ट ऑफ ऑल आई टोल्ड यू दैट any transfer of, whenever there is transfer of heat is there, a transfer energy in the solid, okay, they are only longitudinal waves are important. Okay, because longitudinal wave can carry energy faster. There will be transfer waves also, but the contribution of transfer waves are very less. Okay, so main thing is your VL, because it will carry more energy. Okay, of course VT will be also carry. This is very less contribution. Okay, this is optical. So ये तो एक ही जगह पे ऐसे वाइब्रेट होते रहते हैं. So these vibration do not carry energy. Okay, other transfers they carry very less energy compared to this longitudinal. Okay, so you can take all the energy carried by one longitudinal only, so you can at only 3 V naught by 1 upon V naught equal to 1 upon VL. But I'm just taking what actually what they have suggested in literature, that is the and this V naught is the actually average of these two branches. Okay, so now things are very simple. Now just you need to calculate the total energy. So total energy, how can you calculate? You have to write the density of states. Okay, if you know the density of states, okay, then you can multiply by this average energy already you know, just integrate and you can get total energy. How much time is left? Okay, so we can just start the derivation. We won't able to complete here today, but we'll do tomorrow. Okay, so now things are very simple. Okay, now let me write, okay, density of state. Okay, density of states for solid. Okay, for solid, 3-dimensional solid, 3D. Okay, so gk dk, what is the value? V upon 2 pi square, फिर क्या आगे? K square dk. Very good. But this is only for atoms. I told you there you have to multiply by what? Polarization. Now 3 branches are there. Okay, so I will multiply by 3 here. Okay, 3 is what? 3 is your branches, polarization. Okay, or due to 3 branches, due to 3 branches.
जितने ब्रांचेस आ रहे हैं उससे हमें मल्टीप्लाई करना है.
हाँ बस. So now you have this GK decay. Okay, now you have GK decay. Now you have relation also, omega equal to omega naught k. Okay, so you just find out GW G omega d omega. Find out G omega d omega. What is G omega d omega? Okay, so if you will find out G omega d omega. So you have 3 V 2 pi square. Okay, now if I differentiate this one, d omega equal to V naught dk. Okay, so k square will be what? K square will be your omega naught square, V naught square, and dk will be what? Dk will be your d omega upon V naught. Okay, so what I will have 3V 2 pi square omega square V naught square V naught cube d omega. Okay, so are you getting what I'm doing here?
Yes, sir.
Okay, so now you have the density state expression. Okay, now how many modes are there? If there are n atom, this is the density of modes. Okay, total modes are how many?
FP. FP.
Suppose if I remove this one, this GK DK is equal to what? Total number of modes equal to what?
Number of Ks, no, sir. Total number of Ks equals to number of modes.
Number of Ks equal to number of modes, and number of modes equal to what? Number of lattice points. Okay. So number of lattice point, that means here we are taking monoatomic solid. So lattice point is equal to number of atom. Okay. So here the total number of mode will be how much? 3n. Okay. GK, if you integrate GK DK, it will give you total number of K states. Total number of K states equal to what? Total number of lattice point. I have told you to write that one also. And I'm in monatomic acid, this will be equal to, so we have a, so if I integrate this one, so if I integrate this G omega d omega, okay, from 0 to Vd, I should get, this will give me what? Total number of modes, and total number of modes equal to what? 3n. N is the atom. One dimensional N is atom equal to total number of modes. Three dimensional you have to, because three branches are there. So we have 3n modes. Okay. So now this should be equal to 3n. And this is the what? This is the cutoff frequency. Omega d is the cutoff frequency. Omega d is the cutoff frequency in that dispersion curve. What we have assumed linearly assumed linear curve. Okay. So Debye says only frequency can be from 0 to maximum frequency up to WD, not W0. What Einstein suggests, very high. That is going in optical region. Okay. So he says only we'll use linear curve, acoustic waves, and that is also up to VD. Okay. Now put this value and calculate the Debye cutoff frequency formula. Okay. Put this values here. So if I put this value here, I'll get 3 V upon 2 pi square. Okay. 1 upon V naught cube is constant. Okay. And if I integrate this one, this will give me omega q upon 3 equal to 3n. Okay. So, and this is my d cube, Debye frequency. If I solve this one, so now what is the value for Debye cutoff frequency cube? 3 cancel. Okay. So this becomes 6 pi square V naught cube. Okay. 6 pi square n upon V and V naught cube. Okay. And if I calculate Debye frequency, this will come out 6 pi square n upon V. Okay. Power 1 upon 3 V naught. So this is the formula for Debye cutoff frequency in 3D solid. In exam they'll ask for 1D solid what is cutoff frequency, 2D solid what is cutoff frequency. So for the timing we have just calculated the 3D. We'll calculate for 2D and 1D also. So this is what Debye frequency. Debye frequency. Okay, for 3D solid. Okay. Now,
Sir, in these, okay, I got it.
Okay. Now we need to calculate the energy. Okay. Now we have a modes. Okay. We have modes, and every mode has some energy. Okay. So I need to calculate total energy. Okay. So if you have written this one, I can erase this one. Okay. Now I want to calculate total energy. Once I know the total energy, and then it is very simple. I have to differentiate with certain temperature, and I can calculate the specific heat. Okay. Now, okay. Now what I'll do, I'll calculate the total energy. So total energy will be what? Total energy will be my E. Okay. E will be what? Average energy of per mode. Okay. Average energy at frequency omega. Okay. And GW dW. Can I write total energy like this? Okay. and this EW already you know. Average energy depends on frequency. How? Just now we calculated. This is h cut omega naught, E h cut omega naught, kBT minus 1. So यहाँ is written omega, so we let omega. So this is average energy. So each mode, each frequency have energy. Okay. So there are range of frequency, and I'm multiplying each frequency with the average energy. So each frequency have a you have this thing. Okay, and this frequency varies from where to where? 0 to WT. So this will give you total energy. Okay. So we'll calculate this one tomorrow. Okay. So this expression energy will calculate tomorrow. Okay. You try your own. You can put the values. We have given these values. Omega t value already you know. G omega d omega also you know. Okay. Just you need to integrate in different temperature limits. Okay. So if we differentiate in different temperature limits, we'll get the variation. Okay. So I'm stopping here. Any question?
Sir, why we calculate with average velocity here?
Average energy, na?
नहीं सर, वो जो V नॉट है, V नॉट तो सर ट्रांसवर्स वेलोसिटी और लॉन्गिट्यूडिनल वेलोसिटी का कॉम्बिनेशन है.
हाँ.
हम एवरेज वेलोसिटी लेकर पूरा कैलकुलेट किया है.
हाँ तो उसको एवरेज मांग
सर ये
उसको क्या करेंगे भी? अब जैसे यहाँ पर ये वेरिएशन आपका यहाँ वेरिएशन है. ओके, ये वेरिएशन है ना. ओके, ये वेरिएशन है, तो ये वेरिएशन है, ये वेरिएशन है, ये वेरिएशन है. तो इनका स्लोप लेंगे सबका. ओके, तो स्लोप इसका कुछ वैल्यू है, इसका कुछ वैल्यू, इसका कुछ वैल्यू है. तो तीनों का तीन वैल्यू नहीं ले सकते हमने. 3 वैल्यू लेके उसको एक ही वैल्यू करके कर दिया, एवरेज करके कर दिया हमने. नहीं, इसको फिर अलग अलग भी कर सकते हैं. ऐसा नहीं कि जैसे तुम बोल रहे हो ना कि why we took average. Okay, so that is correction to Debye model. Okay, that is also done. So first we calculating average energy. We're doing this one, but if you want, there is also you can do correction in Debye frequency also. But we just want variation, na? We don't want exact thing. Okay, exact is Debye. And see, actually theoretical value Debye also cannot predict. इस टेम्परेचर पे कितना वैल्यू स्पेसिफिक हीट का. दैट इज ओनली गिव यू approximate values. Okay, it will give you variation, how it varies, and approximately good fit. Okay, if you want exactly correct fitting or point by point fitting, then you have to do like you're saying, and there may be more of the corrections also. Yes.
Okay. सर और एक सर ये जो स्पेसिफिक हीट का जो कंट्रीब्यूशन है हम K tends to 0 पर ले रहे हैं.
हाँ,
मतलब सर बाहर अलग जो K वैल्यू है, जब हाई टेम्परेचर पे ये कोई सॉलिड को हम हीट करेंगे तो रेस्ट ऑफ द एनर्जी क्या इलेक्ट्रॉनिक एनर्जी
वही तो बात है ना भी. जैसे कितना K लेना है. पहली चीज तो है कि लॉन्गिट्यूडनल का कंट्रीब्यूशन ज्यादा है. अब तुम बोल रहे हो कि सर हाई टेम्परेचर अब वो डिपेंड करता है मटेरियल टू मटेरियल ना. जैसे इफ यू टेक डायमंड, तो उसको तो कितना हाई टेम्परेचर चाहिए, तो वो वो के लिए कितना टेम्परेचर हाई चाहिए, वो तो मटेरियल पे डिपेंड करता है ना. उसकी बीटा अपन एम पे डिपेंड करता है ना. ठीक है. तो जनरली जो एक्सपेरिमेंटली जो हम जिस रेंज में हम काम करते हैं, वहां पे वो जो कंट्रीब्यूशन आता है वो उस लीनियर रेंज में आ जाता है. ओके, जो के आप जो एनर्जी बोल रहे हो वो वहीं तक ही पहुंचती है. समझ रहे हो ना. वो उसके आगे के को, क्योंकि उसके लिए बहुत और ज्यादा टेम्परेचर चाहिए. इफ यू वांट मोर बिगर के, उसके लिए और टेम्परेचर ज्यादा चाहिए होता होगा. ठीक है, वो डिपेंड करता है मटेरियल टू मटेरियल. सो हमारा जो मेनली आ जाता है वो लीनियर कर्व में आ जाता है मोस्ट ऑफ द कंट्रीब्यूशन. तो इसलिए उसने इसको लिनियराइजेशन लिया इसको उसने. ओके, आर यू गेटिंग? ओके.
और सर मतलब सर जब हम एनर्जी देंगे कोई मटेरियल को, लाइक हीट एनर्जी मटेरियल को देंगे, तो लो मतलब एनर्जी को कैसे डिस्ट्रीब्यूट हो रहा है उसमें, तो फर्स्ट तो
एनर्जी मोड्स में
करेंगे
एनर्जी
जो एटम
एनर्जी मोड्स में होगी ना, ठीक है। एनर्जी तो एनर्जी जो भी एनर्जी दोगे वो सारी सारी मोड्स में जाएगी, उसकी जितने मोड्स है ना, ठीक है। अब वो तो वो कैसे बता पाएंगे कि ना, जैसे कई सिस्टम होते हैं उसमें जो इस पे तो नहीं कह रहा हूँ, बाद में कई सिस्टम ऐसे होते हैं वो उस डिपेंड करते हैं उसमें वो जो मोड्स एक्साइटेड तब होते हैं जब आप एनर्जी ज्यादा दोगे। ओके, देयर आर लोअर एनर्जी मोड, हायर एनर्जी मोड, हियर आल्सो वी आर रिस्ट्रिक्टिंग मोड अप टू ओमेगा टी ओनली ना। ओके, so there's a big frequency range. Okay, I told you there are k and k states. Okay, तो सारा फ्रीक्वेंसी तो हम गए नहीं, हम पाई वे तक तो गए नहीं है। whatever energy you are giving that will excite the modes, this vibration, this different modes. Okay, that depends on energy. So we are restricting our mode also up to this Debye cutoff frequency.
Okay.
Okay, so tomorrow I will do today my this marker not working. Okay, my ink also finished 5-6 marker, they are not working. Okay,
सर
हाँ
हमने ना यहाँ जो ये किया ना वो नहीं, मतलब इंटीग्रेशन में 0 to मतलब वहाँ इंटीग्रेशन मतलब क्या कर रहे हैं वो समझ यहाँ नहीं। इसके पहले हमने एक एक्सप्रेशन लिखा था 0 to WD G ओमेगा इज इक्वल टू 3n।
हाँ, so
नंबर ऑफ मोड्स दिखा रहे हैं
भी ये क्या है, जी ओमेगा क्या है, डेंसिटी ऑफ मोड्स है ना,
यस सर।
एंड जी ओमेगा टी क्या है, डी ओमेगा रेंज में कितने मोड्स हैं।
हाँ
सो अगर मेरी मैक्सिमम फ्रीक्वेंसी ये है तो ये कितने टोटल नंबर ऑफ मोड्स हैं,
हाँ
टोटल
इज
नंबर ऑफ
इक्वल
मोड्स
टू टोटल नंबर ऑफ आइटम्स। ओके
3n है।
क्लियर।
ओके, तो ये जैसे ये रेंज है। ओके, in this small range how many frequencies are there and what is the energy. Okay, so this is density of states na, this is density of states, different is this omega 1, omega 2, omega 3, every frequency there are number of states are there. Okay, and what is their energy, e omega 1, e omega 2, e omega 3, and then we are summing this all the things, and because it's continuous spectrum, instead of summation we are putting integration. Are you getting my point what I'm saying?
Yes sir, clear.
Okay, so I'm stopping here. Thank you very much for being patient. Okay,
Thank you, sir.
Thank you, sir.
thank you.
Thank you, sir.
Thank you.